They got a STAT1800 chi-square test. The previous video, if you just watched it, your head's probably spinning and you're thinking that this chi-square stuff's going to be pretty challenging. I don't think it will be. I think this video will kind of prove that to you. So let's get started. Okay, couple of things. If we go to Google Chrome and if we go to handouts, there's a under content there's the folder called handouts, and if you go to the very bottom, you find a file called Party, Belief, and Gender. Now, if you download that, let me actually get out of this. I've actually downloaded it to my computer. It's a semi-interesting data set, at least I think it is. It was really collected. I haven't tinkered with it at all. So we have three variables. We have party, either Democrat or Republican, and I think we've got a really large data set, maybe 900 or so, 880. So we have Democrat or Republican, and we also have on the subject whether they're pro-life or pro-choice, and we have their genders. So if we scroll down and just kind of take a random person, we can see that the person at line 336 is a Democrat, they're pro-choice, and they are female. All right, so I'm going to close this down, and it's on my desktop, which is good. That's where I want it. And now I'm going to go to StatCrunch. So guys, I want to go to my computer and load a data set. And I want to choose the file. And obviously the file is party, belief, and gender. And again, I don't really know what's going on with this down here, and I really don't care. But I can load the file. Now, guys, this is going to be one of the few cases where you're going to have raw data. You're not going to have a summary. You're going to have the data set. So, guys, let's just take a look at some of this. So, if I wanted to go to stat and summary stat and columns, well, I can't do that, can I? It's got to be quantitative. So, if I go to stat and go to table and do frequency, then I could put party in, and I could compute, and I can see that 550 of the 880 are Democrat and 330 are Republican. So 62.5% of my sample is Democrat and 37.5% are Republican. I also can go stat, tables frequency, and I could look at belief, and let's just go ahead and throw in gender as well. So looking at these separately, I see that 480 or 54.5% of the sample is pro-choice, and I can see that 400 out of the 880 or 45.5% is pro-life. Gender, pretty equally spread, 450 versus 430. So the sample is almost equally split across females and males. But guys, the most interesting part of this actually comes when we go to stat, we go to tables, and we look at the contingency. So guys, this is going to be one of the few cases where you're going to have contingency with data. Now, my focus right now, when we do contingency tables, we're looking at the relationship between two variables. Again, I have three variables here, so if I want to analyze these three categorical variables, I have to use something called log linear analysis. Don't even write that down because we don't go there. My graduate students, I teach a section on log linear analysis, and it's their least favorite section because it's just complicated. So we're going to keep it simple, and all of our contingency tables are going to deal with just two variables. So the two variables I'd like to look at right now are party and belief. So I go with data. So my row, I'm going to do party. In my column, I'm going to do belief. All right. I want the expected cell count, and I want to do a Fisher's exact test for independence, because what I have is I have what's called a 2 by 2 table. Why is it called 2 by 2? Well, one of the variables political party is either Democrat or Republican, making it a two possible outcome. The other variable is belief about abortion, pro-life, or pro-choice, giving two outcomes. So it's a 2-by-2 table because each of my two categorical variables has two possible layers, if you will. So now I'm going to compute this, and let's see what I get. Well, I get a lot of stuff here, don't I? First of all, I get the contingency table, and what I've got there is I've got the, and I'm going to write all this stuff down over. So I've got Democrat, Republican, and I have pro-choice, pro-life. Now I'm looking at the numbers in the cells that aren't in the parentheses. So I have 400 Democrats who are pro-choice, and I have 150 Democrats which are pro-life. Of the Republicans, 80 are pro-choice, and 250 are pro-life. Now, the values in the parentheses are called the expected cell counts. And I'm going to write those down. So I have 300 is the expected cell count for Democrat choice. I have 250, the expected cell count for Democrat life. And I have 180 and 150 for Republican life. So the 150 is the Republican life. And guys, I have a total of 880 subjects in this study. All right. So guys, this is one of those things, this is one of those illustrations where you really got to be with me. We're gonna do a lot of calculations here. It's not going to be something where you're going to be able to prop up your feet and have Modern Family on or whatever you like to, or a movie. This is something where we're really going to have to connect. All right, gang, let's go here, and I want to do some calculations for you. Now, the first thing that we would do is I would question number one, how did they get the 300? How did they get that expected cell count of 300? Well, guys, in the previous video, I told you that we could take the expected cell count as taking the row total times the column total over the sample size. Well, if I focus on this cell count alone, my row total is 400 plus 150, which is 550. And my column total is 400 plus 80, which is 480. And my total is 880. So I'm going to take the row total, which is 550, times the column total, which is 480. And I'm going to divide by the sample size n, which is 880. Now let me see if I can find my calculator. My daughters are now, here it is, taking algebra and probability and all that crazy stuff in the 8th grade. So they steal my calculator a lot. So anyway, guys, if we take 550 times 480 divided by 880, we'll see that we get 300, which matches perfectly, as it should, with the expected cell count for the Democrat who is pro-choice. So if we do that again, if we would do it, if we were focusing on the expected cell count for this cell, we would take what? We would take 550. 150 plus 250 is 400. So we take 550 times 400 divided by 880, and I guarantee you we're going to get 250. Now, getting the expected cell count, why? Why do we care about that? Well, here's the way the process plays out with the chi-square test of independence and chi-square test of equal proportions. So our null hypothesis in this case would be that the percentage that are pro-choice is the same as the percentage who are pro-life. And the alternative hypothesis will be that these two are not equal. Just like we always do, we establish our level of significance, and again, it's typically 0.05. Some of you get so focused on 0.05 that if it changes in the problem, sometimes you don't recognize that. And hey, I do it too, because it's just so often the alpha value is 0.05. So we have to read the problem and make sure they haven't changed it to 0.01 or 0.10. Anyway, what does the expected cell count tell us? It tells us that if H sub O is true, we would expect 300 to be Democrat and pro-choice. And why 300? That's the expected cell count. So the expected cell count is under the null hypothesis, under the true null hypothesis. This is what we would expect to get kind of at random based on the 880 sample that we have. Well, the chi-square statistic is all about comparing the observed minus the expected squared over the expected for each of these. So we're going to sum these up for each cell count. So guys, for the first cell, you go back and look, our observed count was 400, our expected count was 300, square that over 300. Our second cell, and I'm looking now at the Democrat pro-life, our observed was 150, our expected was 250 over the expected. Our Republican pro-choice was 80. There was 180 that was the expected. In the final, we had an observed cell count of 250 minus the expected of 150 over the expected. Now let's do each one of these, just so I want to make sure everyone is on track with me here. When I put the first, I get 33.33, right? The next one I get 150 minus 250 divided by 250. So I get 40. This third one I get 80 minus 180 squared divided by 180. So I get 55.55. 56 actually. And the last one I have 250 minus 150 quantity squared divided by 150. And I get 66.67. Now if I add all those up, I get 33.33 plus 40 plus 55.56 plus 66.67. I get 195.56. Now let's go back to our StatCrunch output. And we're going to actually have to run this again. Let's go to session results contingency table, and let's go to edit. And I want the chi-square test for independence. And you can see that when we run the chi-square test of independence that we get this value of 195.55, which we just calculated by hand. So the chi-square test statistic is the sum of the differences between the observed cell count and the expected cell count, quantity squared in the numerator, divided by the expected cell count. Now, let's go back over, and we can see here that we have chi-square degrees of freedom 1. So our degrees of freedom can always be found by the number of rows minus 1 times the number of columns minus 1. Well, in this case, we have 2 rows because we have Democrat and Republican. We have 2 columns. We have pro-life and pro-choice. So you can see how they get the degrees of freedom equal 1. So guys, what we're dealing with here is we are dealing with the chi-square distribution. Degrees of freedom 1. Now, we're testing a 0.05, so there's some chi-square critical that separates the reject and the fail to reject. What is it? Well, guys, it's easy to find with StatCrunch. It'd be hard as heck to find without StatCrunch. So guys, we go to Stat, we go to Calculator, and we go to a new selection that we haven't used before called chi-square. But it works the same as the other ones. All right, degrees of freedom 1. Well, and we want the area above a particular value to be 0.05. So our test, our chi-square critical is 3.841, let's call it. So going back over here, our chi-square critical is 3.841. So if we get a chi-square statistic, anything bigger than 38.41, then we reject the null. Otherwise, we fail to reject the null. Well, guys, ours was huge. Our chi-square stat was, what was it, guys? 70, 100 and something, I forget, 195. Let's just call it 196. So guys, that's way out here, right? So we have statistical significance and we reject the null hypothesis. So, so guys, can't find my null. All right, here we go. So the null hypothesis we would reject, and we would conclude that the percentage of those who are pro-choice is not the same as the percentage who are pro-life. Now, we can even conclude something else. If we look at this as a contingency table, our null hypothesis would be that belief and party are independent. Our alternative hypothesis is belief and party are dependent. Guys, independent means not related. Dependent means they are related. So guys, works the same way. That's the cool thing about chi-square test of independence, or whether we're testing the quality of two proportions. Same thing, guys. Our chi-square has degree of freedom 1. And it's going to be 195 point, whatever it was, 195.56. and our p-value is extremely small. Now, this is kind of a boring, well, not boring, but it's just so large that we're not really going to get much of a indication about the p-value. But nevertheless, I'm going to show you how you would calculate that. So guys, what you would do there is you'd use the same degree of freedom 1, but you'd put in your value of 195.56, and you calculate the area above it, and you can see that it just reports 0. It's really not 0 because there is some area under the curve to the right of 195.56, but the number is so small that it registers as a 0. So guys, I'm going to do some other types of problems. I don't know. Let's just look at one right now. Let's look at to see if there's a difference in gender across belief. So I think it's going to work better if I do this. In fact, I know it will. Let me get that, and let me get this. So I can write. So guys, what I want to do now is I want to investigate is a relationship between belief and gender. So belief and gender are independent. Belief and gender are dependent. Guys, just for the heck of it, just for something different, let's set our alpha at 0.01. So how are we going to proceed? We're going to calculate our chi-square statistic. We're going to calculate our p-value. And then we're going to make our decision. So guys, over here, I'm going to go stat. Couldn't find it. Go to tables. I'm going to go contingency, and I have with data. So my row variable is going to be, I'm just going to put belief on the row, and my column is going to be gender. I want my expected cell count, and I want to run my chi-square test for independence. Now, you'll find out when you study these things much that the Fisher's exact test is a lot better when you do a 2x2, but it will only give you the p-value. So if we want the chi-square test statistic, we have to make the selection chi-square test for independence. Okay, compute. What do we look at? Our chi-square value is 0.0055. And our p-value is 0.94. So our p-value is greater than our alpha of 0.01, so we fail to reject. Telling us that belief and gender are not related. And we can actually go in and make it a little bit more interesting and look at the percentage who are, actually, we can just look at it right here, can't we? We can see that if we look at the proportion of those who are pro-choice and across gender, we have 480 out of 880 and 400 out of 880 who are pro-life. So there's not enough difference there for significance across the percentage who are pro-life and the percentage who are pro-choice when separated across male and female. All right, gang. Next video, I'm gonna shake it up a little bit, and and go from there. So take care.